Good morning, and I'd like to thank Sylvain Mistracci, the Agricultural Counselor, for inviting me. I am glad to be able to participate through a remote sensing presentation. The title of my presentation is Soil Organic Carbon for Climate, Food, and Other Ecosystem Services, which is part of the subject matter at the title of the conference, Soil Health Practices, Common Ground on Experiences and Knowledge. I'd like to begin with giving the definition of soil quality and soil health. The term soil quality or functionality is not exactly synonymous with soil health, and they should not be used interchangeably. For example, soil quality functionality is related to soil functions or what it does, whereas soil health presents the soil as a finite and dynamic living resource. Soil health is directly related to health of plants, animals, people, and ecosystems. The resources used for agriculture is something that we need to consider very carefully. For example, 40% of the Earth's terrestrial surface is used for agriculture. 75% of the agricultural land, 3.73 billion hectare, is allocated to raising animals. 70% of the global freshwater withdrawals are used for irrigation. 30 to 35% of global greenhouse gas emissions are contributed by agriculture. And in spite of all that, 1 in 7 persons is food insecure, and 2 to 3 in 7 are malnourished. Thus, this is the right time for a paradigm shift. Soil health and management have a great role to play in sustainable natural resources management. With severely degraded soil health, productivity cannot be enhanced by improving just one factor at a time, such as soil fertility cannot be managed just by adding chemical fertilizers. Soil compaction cannot be eliminated just by deep plowing. The drought cannot be mitigated just by flooding the soil. Soil erosion cannot be controlled just by installing terraces and other engineering devices. Soil acidity cannot be neutralized just by liming. These are symptomatic treatment of the problems. Therefore, meeting the food demand by 2050 needs a very careful consideration. Indeed, the world produces enough food to feed 10 billion people. Thus, the food and nutritional security must be achieved by reducing waste, which is 30 to 50%, increasing access to food by addressing poverty, inequality, wars, and political instability, improving distribution of food, increasing uses of pulse-based and plant-based diet, and identifying alternate sources of protein, accepting personal responsibility of not taking soil, natural resources, agriculture, and the food for granted, and of course increasing agronomic productivity from existing land, restoring degraded lands, enhancing biological nitrogen fixation by legumes, and converting some agricultural land for nature conservancy without any additional conversion of land to agricultural ecosystems through sustainable intensification and restoration of soil health. The idea is no additional appropriation of land and natural resources to agriculture. That brings us to the definition of soil organic matter. Soil organic matter is the organic component of the soil and comprises of plant and animal residues at various stages of decomposition, cells and tissues of soil organisms, and substances synthesized by soil biota. It consists of 4 primary components: the living organism, which are about 5% or less, the fresh residues, about 10%, the partially decomposed or inactive fraction, about 33 to 50%, and decomposed organic matter, 33 to 50%. Out of all these, the living organisms constitute 5%, are really the needle of the eye through which all the organic matter must pass. Now, if we look at the dynamic of soil organic matter upon conversion of natural to agricultural ecosystem, soon after conversion, there is a decline in soil organic carbon concentration to about 50% within the 50 years period in the temperate climate and maybe 5 to 10 year period in tropical climate. The soil organic carbon concentration can keep declining further if the soil is prone to accelerated erosion by water and wind. If not, it reaches another equilibrium. At this point in time, if we convert to improved recommended agricultural practices, it can increase the soil organic carbon concentration to another higher level, which may reach equilibrium in another 20 to 25 year period. And at that point, if we adopt another improved practice, it can be further increased to the maximum level of the original or antecedent concentration of carbon. It is possible in some cases to go beyond that level by adopting more innovative technology, which in some cases, which these initial conditions have limitation, this is possible. A typical example would be acid savanna soils of South America, or drier soils with deficiency of water, or soils with deficiency of calcium, magnesium, or phosphorus, for example. In general, by understanding this, we can calculate the slope of the line, delta y over delta x, that indicates the rate of carbon sequestration. We can also assess the carbon sink capacity by the current level to versus what the original level was, and we can also define the mean residence time by dividing pool of carbon over flux. Then we can identify the cultural practices which can be used to achieve this attainable potential or the maximum potential, and these practices have their own carbon footprint. These practices vary from site to site, from place to place, and there is no one single option that can be universally applicable. Important among these practices are conservation agriculture, the biochar, agroforestry, desertification control, the afforestation, the pasture management, water harvesting, fertigation, drip sub-irrigation, farming system, and so forth. The idea is to identify the site-specific practices and to assess the carbon footprint of these so that from the global rate we can assess the net rate of carbon sequestration. The estimates of the global soil carbon debt vary, but common consensus recent publications by Sunderman and colleagues estimate about 133 petagram. One of my publications we have estimated 135 petagram. There are a few others which indicate similar kind of estimates, somewhere between 120 to 180 petagram of carbon lost from soils of the world since the beginning of agriculture. If this carbon can be restored in the soils, this means the total drawdown potential of CO2 of about 60 to 65 parts per million. And this drawdown can be achieved through sustainable intensification. The idea is to produce more agronomic production from less land, from less water, from less consumption of fertilizer and pesticides, from less use of energy, and from less emission of greenhouse gases to the atmosphere. The goal is to produce more from less through sustainable intensification. And this can be achieved by replacing the nutrients which are removed, by responding wisely to what is changed, and predicting what will happen from anthropogenic natural perturbations, and by enhancing soil resilience, which can be enhanced by restoring the soil organic carbon concentration in the soil or the soil health. There are certain issues which need to be addressed, and addressing the food demand, especially of the increasing population, which in this line 1 is in billion at a global scale, and this billions of population means increasing from 6.4 billion in 2005-7 to 9.7 by 2050, 10.6 billion by 2080, 11.2 billion by 2000. The general feeling is that we need more land and more water resources. I would like to propose that we have enough allocation of land and water resources, and the increasing demand and caloric needs of the population from about 2,700 in 2005-7 to 3,017 2050 to 3,200 in 2080 to 3,300 in 2100 can indeed be met from lower land resources than allocated present. It is feasible, though, that this total cereal production of 2,000 million tons at the moment may be increased to 3,000 by 2050, 3,350 million tons by 2080, and 3,540 million tons by 2100. However, the cereal land needed for this production doesn't have to be increased. I strongly believe that the present cereal area of 630 million hectare can be reduced to 600 by 2050, 560 million hectare by 2080, and only 500 million hectare by 2100. Similarly, the nitrogen fertilizer, the total fertilizer use, can be reduced from 200 million tons at the moment to 160 in 2050, 120 in 2080, and only 100 million tons by 2100. Yet the desired crop yield of cereal can be increased from about 3,300 kg in 2005-7 to 5,000 kg in 2050, 6,000 kg in 2080, and 7,000 kg in 2000. The goal is to produce more from less land area, less fertilizer consumption, and at the same time increase the crop yield by using the best land, by best practices, so that we can save the land for nature and nature conservancy. That's the strategy of improving soil health. I'd like to conclude again indicating the importance of restoring soil carbon and soil health through the management of soil organic matter, because depleting soil organic matter and declining soil fertility, degrading soils and denuding lands, recurring drought and intensifying heat waves, increasing salinization and reducing use efficiency of water, low crop yields and perpetual hunger, marginal living and desperateness are as real threats to global peace and security as are ICBMs and nuclear weapon proliferation, because the health of soil, plants, animals, people, and ecosystem is one and indivisible. I wish you all a very happy discussion, and thank you for the invitation to participate.